record button and share my screen, and we're gonna jump in. Come on, Zoom. All right. So we're still talking about conjugated dienes, and we've talked about reactions of conjugated dienes and what conjugation is and why it's important, and how it happens and how you get molecular orbitals from atomic orbitals and all that stuff. So one of the reactions that we talked about is cycloaddition, right? We talked about that, the Diels-Alder, and how it happens and what the transition state looks like. And today we're going to talk about addition of HX to a conjugated diene, right? And it's a couple of points about this addition of HX that I want to make right up front. And the first thing is you get two products. My finger is sticking to the screen because I just washed dishes, so sorry. All right, you get two products. The second thing is that it's temperature dependent. Right, so your product distribution of those two products that you get is dependent on the temperature. You can do the reaction at low temperature to favor one product and high temperature to favor another product, or higher temperature, increased temperature. So at low temperature, that's going to give what we call the kinetic product. And I'm abbreviating product as PDT, so no panic about that. And then at higher temperatures, it's going to give you what we call the thermodynamic product. Right, so the thermodynamic product and the kinetic product, that's really going to be one of our major topics that we cover when we talk about this reaction. And then we're also going to talk about some of the features like the reversibility or irreversibility of the reaction. But all of that's going to be covered when we talk about the thermodynamic product versus the kinetic product, right? The kinetic product is irreversible, and the thermodynamic product is, let me not do that, it's reversible. That's my shorthand for reversible, RVSBL, because I didn't want to run out of space. All right, any questions so far? Let me add another page in here right quick. All right, so let's look at an example of the reaction. And we're going to talk about the mechanism, of course, and how the reaction happens and why you see those two products. All right, so let's take a simple conjugated diene like this. And we're going to react it with HCl. All right. Now, I know you remember this from part one, where when you react, I'm gonna put this in a box. Let's say you react a simple alkene with HCl, right? The product that you get out is here, right? Alpha halide. Where, let me run through the mechanism right quick. Change the color. Where you have the, too light, sorry. You have the alkene attacking HCl, right? Doing a proton transfer. And then the HCl bond breaking, those electrons going with chlorine. And then before you get to the product, all right, you get this carbocation intermediate. With the carbocation being on the most substituted carbon, following Markovnikov's rule, and then the H ending up here. All right. Do y'all remember that from part 1? I'll take that as a resounding maybe. All right. Then the chlorine attacks at the plus charge, like so, and end up with the alkyl halide. All right. So that mechanism, nothing changes about that when you're dealing with a conjugated diene. Right. It's the same mechanism. The difference is the type of intermediate. So this reaction will always go through a allylic carbocation. Hold up a second. All right, so that allylic carbocation for this reaction is a common intermediate. That's where both of your products are going to come from. All right, so let's look at how it happens. And again, that's just a review. It's the same, same mechanism. So if we take a conjugated diene plus HCl, that's going to react like so. Right, the alkene is going to be nucleophilic and is going to attack HCl just like we saw in the example above, right? So the key is the intermediate. Intermediate is going to look like this. All right, so you got this carbocation, this allylic carbocation. Right? Why? Somebody tell me why you think the allylic carbocation is going to be the favorite intermediate? Because where else could I put the plus charge?
You could put it on the primary.
I could put it right here, couldn't I?
Yeah.
So why do you think the allylic carbocation is favored?
Because it's on a secondary and adjacent to that double bond.
Exactly. Exactly. With it being adjacent to a double bond, that means that I can stabilize it through resonance. Is that right? If I push this pair of electrons here, following? So I can stabilize that cation through resonance, and it is on a secondary carbon. So let me put that in here. That is resonance stabilized. right? So it's resonance stabilized. So that's the intermediate that chlorine is going to attack. All right, so chlorine that we got from HCl is now my nucleophile, right? So it can attack here directly right? You can have direct attack at the plus charge, at the carbocation, or it can attack here. Right? And push that double bond over. Right? It can attack both positions. It can attack both the directly at the plus charge, or it can attack at the alkene. I like to call this attack resonance attack, right? Because that's where the plus charge would be if you drew the resonance form. Right? Anybody not see that? Like if I drew the resonance form, it would look like this with the plus charge out here. Right? What you'll see in the video and what you'll see in your textbook is that when it attacks directly, this is called 1, 2. And when it attacks at the alkene, this is called 1, 4. Right? Normally, the way that I explain the 1, 2 and 1, 4, because people always get really confused by it for some reason, but it's arbitrary. If I label this like that, then my carbocation is going to be here, right? If I label it the other way and start numbering on this end, then the carbocation will be here, right? It just depends on how you number it. But that's where the numbering comes from, the 1, 2 and the 1, 4. That's where it comes from. The fact that if you number the conjugated diene, then the allylic cation is either going to be at 2 on one end or it's going to be 2 on the other end, but it's still going to be at the 2 position. All right, any questions so far? Anybody stuck, not seeing it, not following? All right. So here's the thing about let me fix this chlorine too. I want to upload that to Blackboard looking like that. It's kind of sloppy. So here's the thing about the reaction. So you can favor, again, you can manipulate the product distribution. You can force it to give you mostly 1, 2 product, or you can force it to give you mostly 1, 4 product. It depends on the temperature. So at low temperature, and then we're gonna jump in and do an example real quick. Low temperature is gonna favor the 1, 2 product. Or that will be in the case of this reaction, that will be the kinetic product. And then at increased temperature, because I don't want to say high temperature, because you can increase the temperature by 10 degrees and then increase the rate of that other reaction. That'll give you the 1, 4 product. So I'm gonna say increased temperature. So increased temperatures are gonna cause the 1, 4 product to become favored. The reason why we can say the 1, 4 product is favored. I didn't draw the products either, but I'll draw them in. Right? If you look at the resonance form right here, you can see that that's a disubstituted alkene. Right? That alkene is going to be more stable. So that's why we call that, that's why we would call that the thermodynamic product. Right? Because you get a disubstituted alkene, and that's more stable than a monosubstituted alkene, which is what you get from the 1,2 product. Right? I didn't draw the products in, so let me do that over here right quick, and then we're gonna move on to another section where we can actually work through one of these problems. So that's one product. That's the other product, right? So this will be your 1,2 product, and then this will be your 1,4 product. All right. Any questions about anything so far? All right. Let's jump to an example right quick. And the top reaction is, it says consider the following reaction scheme and draw the product. And does anybody remember what DBN is? It was on the exam, I think. Or DBU was on the, one of them was on the exam.
Isn't it a leaving group or something like that?
It's actually a strong base.
Yeah, base. See.
Triplate is a leaving group. And if I have a strong base and I treat this alkene, what do you think is going to happen? Let me put some electrons on the base, that might help. It's going to do an elimination.
Yeah.
What type of elimination is that? Anybody remember?
E2.
Yeah.
E2. Because of the base, right?
Mm-hmm.
If you have a strong base present, and it's going to be E2 elimination. So that product is going to look like this. Come on, Russell. Here and then here. Is that right? So that's the question at the bottom is the product a conjugated diene? That's just my way of making sure that you don't forget stuff. What do you think? Is it conjugated?
Yes.
Yeah, it is. Okay. It is a conjugated diene. You can see alternating, double, single, double right there. It's not fully conjugated, but it is conjugated. All right. So down here, we're going to work on this thing. And if you notice, I want to make this point too about these reactions. Either one of those alkenes can react. Following? So we're going to start here. We're going to start on this side. I don't know why this thing is lagging, man. All right, we're going to start on this side, with this alkene. So we number this, change colors real quick, as 1, 2, 3, and 4. Follow? That alkene is what's going to attack HBr. So let's think about, well, how do y'all want to attack it? You want to do the products first, or you want to go through the mechanism first?
Mechanism.
All right, let's do that. So let's take this double bond and attack HBr. We're going to break the HBr bond, give those electrons to bromine. So then this is our intermediate. This is what our intermediate is going to look like. right? So we got a here, here, and then the plus charge right here. Everybody agree with that? Or anybody not see it? That's an intermediate. And it's an alylic carbocation. And I know that's, let me say up front, that's probably will be some competition between that and forming that tertiary cation. That's possible too. But for the purposes of this reaction, we're gonna roll with the alylic carbocation because that's the intermediate that we probably we're gonna see in order for this conjugate addition to take place. But it's not, I'm not ruling out that you could form the tertiary. Right? And then plus, Lord have mercy, I can't write a plus sign today. It's Monday. Plus bromine. And it's negative, right? So now the question is, if you look over here, it's, first of all, products is in plural because it's asking for both the products from the attack of the first double bond and then the ones we're gonna get from the second. So we'll fill all that in a minute. All right. So where's bromine? If I do this at 0, which is low temperature, where's bromine going to attack? If I do it at low, yes. If I do it at low temperature, we just said a second ago that the uh, 1,2 product was going to be favored. Is that right?
Yeah.
So here we're going to attack right here at the plus charge, and this is for 0 degrees. All right, and I'm gonna draw in the product. Right, that's the product by attack at 2, at the 2 position. And it's major. At 0 degrees, this is the major product when that first alkene reacts. Right? All right. What is the 1,4 product look like?
You would use the tertiary carbocation? Okay.
So this is only going to happen at the conjugated system.
Okay.
Right? So the bromine is it's either going to attack at 2 or it's going to attack over here at 4. Right? So it's only going to attack either one. It's only going to do 1, 2, or 1,4 attack. Right? So that product would look like this, right? Move that over some. Right, so bromine would be here. The double bond would be here.
Yeah, I got it.
Methyl group is still up there. Is that right?
Yeah.
And this is minor at 0, at low temperature. This is going to be the minor product. All right. Any questions about that? So this is the purple pathway is 1,4. And then the red is 1-2 attack. And at low temperature, a 1-2 attack is favored. Are we following that?
Uh-huh.
And it's important to remember that the allylic carbocation is your intermediate. It's always going to be your intermediate. All right. What about at 37? What if I did this reaction at 37 and I used the same alkene to react? What do you think?
Would just be the opposite.
It would just be the opposite. The major product would be here. I'm just going to copy it if I can. Won't give me the option to copy. And no mind. I'll just redraw it. All right, so the major would be here. This would be major at 37. Right? And then the minor would be the major product from 0, the 1-2 product. All right. Right, so the minor and major products swap based on the temperature. Right, so the product distribution is based on the temperature. And the third, this would be the kinetic and then the thermodynamic product would be here when you increase the temperature. Right, so that's the thermodynamic product. And then the kinetic product at 0 is the 1-2 product. Let me write this in another place. Right? Any questions about that? No questions. Is it just because it's Monday? That's okay. We're gonna make it work. All right. So let's now take a look at if we use the other alkene, what products we would get from that. All right. So I'm just gonna, I gotta erase some of this stuff. I'm just gonna cut this out and put it on another page. It'll let me. Never mind. I'll just draw it. Everything is acting stupid today.
Have you updated Notability lately?
I probably need to. I haven't.
Yeah, they updated it, a huge update.
I need to do that. I'll do it after class though. If I try to do it now, it's gonna be a wrap.
Yeah.
So here's the alkene again. Plus HBr. And then of course we're gonna write the kinetic and the thermodynamic products, you know, so we're still doing it at 0 degrees Celsius, or 37 degrees Celsius.
You
All
have
right.
to shift the double bond over one to the right.
Oh yeah. Did I screw that up?
Yeah.
All right.
The double bond is
It's right here, here and here.
Yeah.
Yeah. All right. Thank you.
Mhm.
All right. So, but now we're using this double bond, right? And we can still number it 1, 2, 3, and 4 like that. And then so when this reacts, use red again. So this is coming here to attack H. And I'm breaking the HBr bond, right? Nothing changes for that. But the intermediate is going to look different. The intermediate is going to look like this, where the plus charge is here, and then this alkene is still intact like that. So that's my allylic carbocation intermediate. And this will be plus Br, and it's negative. All right. So now bromine can attack where? It can attack, I'm gonna use a different color pencil here. So it can attack directly at the plus charge, which would be 1-2 attack, or it can attack here, right? And shift over the double bond. That'll be 1-4 and 1-2. So if we just draw out both products, then we'll see, we can determine which is major and minor based on the temperature, right? So that first product is going to look like this, right? Uh-oh, I gotta move that. It's right on the page. So bromine is here, like that. Is that right? That's going to be my 1-2 product. And that's going to be plus here. And this will be my 1-4 product. 1-2 is here, 1-4 is here. Anybody not see that or disagree? It's still a free country. So for now, so you feel free to disagree.
So you get 4 products then, or
Yeah, it, because both alkenes are just as susceptible to reacting. So you probably will get a mixture of all of these products. But at low temperature, you'll probably get a mixture of, you'll get more of this and the other 1-2 product, right? So those, you form both of those and then both 1-4s, but they'll be in less, they'll be formed in a lower amount because you're at low temperature. Then you increase the temperature, you're going to get both 1-4s as major, and then the other two 1-2 products, you won't see as much, but you'll see some of it. But normally, the way I ask the question is I'll tell you which alkene to use. All right. Any other questions about that? So There's another question on the handout here. Because you can interconvert. That's one of the things about this. One of the things about this reaction is that you can set up a situation where you can set up equilibrium. And what happens is if you do the reaction at low temperature and then warm it up, what you do in doing that is you start to set it up to where you can interconvert between the kinetic product and the thermodynamic product, right? So you can establish an equilibrium by warming the reaction up. You can take the kinetic product and turn it into the thermodynamic product. Right, all of that stems from being able to go back to the intermediate. Right, normally under kinetic conditions, and I can show you down here, and this is in the video too, so it's going to be redundant when you watch it. But under kinetic conditions, right, you're starting at the intermediate, right, and then from that intermediate, you are either going to, I'm gonna say product one, which would be 1, 2 in this case, or product 2, which would be the 1, 4 product, right? So that's the pathway, and at low temperature, this is irreversible. Right, so once you do the reaction and you get to product 1, notice that that product 1, P1, is higher in energy but the activation energy is lower, so it's easier to get to. All right, let me show you that part. The activation energy will be here, right? It's delta G double dagger, right? So the product 1 is lower activation energy, but the product itself is higher in energy. But if you look at the pathway to get to product 2, right, that activation energy is much higher. Right, so that's for product 2, the delta G double dagger is higher, and so it's harder to access. Right. So product 2 has a higher activation energy, even though the product itself is more stable and lower in energy. The fact that you're at low temperature means that you can't access product 2 because you don't have enough energy to get over the activation barrier. So I'm gonna say less accessible. Right, so the higher the activation energy is, the less accessible that product is. And at low temperatures, you don't have enough energy in the system to push that reaction over that hump. You get some of the 1,4 product, but the predominant product is going to be the 1,2 product. Right, but if you're in a situation where you got the kinetic product and you start to warm that reaction up. Then you add more energy to the system. And what happens is you start to set up equilibrium. So it's no longer irreversible once you start increasing the temperature, right? So P1 can interconvert back to the intermediate. And then if there's enough energy, it can go and form P2, which is more stable. Which is the thermodynamic product, right? So up here, that's what this question is talking about. So it says if both products from the reaction done at 0 are warm to 40 degrees, the product distribution changes and the kinetic product is converted into the thermodynamic product. Using the major product from the reactions done at 0, propose a mechanism for how this might occur. All right, so it sounds like a lot, but what it's asking you is how could you go from the kinetic product back to the intermediate, and then from the intermediate to the thermodynamic product. So that's all it's asking. So if you look at the kinetic product, right, and you look at the intermediate, how would you show that if I asked you to put an arrow in or arrows in to show how you did that?
Show bromine leaving.
Hmm?
Could you show like the bond attached to bromine?
You want to show bromine leaving. Okay, let's do that. Right? So that one arrow tells me that bromine left and I'm left with a carbocation intermediate. That's exactly right. Where have we seen that before? We've seen it before.
SN1.
Yeah, SM1 and E1, they both happen the same way, right? Those unimolecular eliminations and substitutions, they all happen like that. The leaving group leaves first, you get a carbocation, right? So the mechanism itself is not impossible. We've seen it before. So you lose the leaving group, and then now what happens to go from the intermediate to the thermodynamic product? What do I need to do?
The 1,4.
Yeah, so I just attack here, right? Here
Yeah.
and here. And when I do that, that's going to get me from the intermediate to the thermodynamic product. And that's what happens when you warm these reactions up. If you do them at low temperature, when you start warming them up, the actual product starts interconverting back to the intermediate to form the thermodynamic product, which in most cases is the most stable product. All right. All right. What would you do for this one? And something different?
Same thing.
Same thing. Kick off the leaving group. All right. So show the leaving group leaving, and then come here and show the bromine attacking. Right. The intermediate. Same exact thing. Right. And again, you can set this situation up by starting the reaction out under kinetic conditions and then warming it up so that you start to see that you start to make more energy available to get to the thermodynamic product, because the kinetic product is irreversible. And if you leave it at low temperature, then you're not going to see that. But if you warm it up, you'll start seeing that interconversion between those products. All right. Any questions about anything so far that we talked about? All right. Let's do let's warm up. Actually, not warm up. Let's take 1644. Let's do A. What do you think? Is A going to give you this 1, 2, and 1, 4 addition? We're not going to do the actual reaction on it. We're going to do C. But I just want to see how you're thinking. Will you see the two products, the 1, 2, and 1, 4 product with a diene like A? Why or why not?
No, I don't think so.
Okay. Why not?
Well, I'm not sure if this is right. It's because is it because it's not conjugated?
Not conjugated. That's exactly right. So these two alkenes in A here and here are going to react independently. There's not going to be a 1, 2 or 1, 4 product. They're just going to react like alkenes would normally react, right? And so for if this alkene was the one that reacted, then we treat it with HBr. We just get this, and I'm gonna draw it. I'll draw it right here. You'll just get this, right? And then if the other alkene reacted, since both carbons are secondary, you're gonna get a mixture of products where bromine will be on either one of those carbons. But you won't see a 1, 2, and 1, 4 because it's not conjugated. All right. Let me see if I can cut C out. Why it's not letting me copy this stuff today? I got room over here. So let's say for C that we reacted this alkene. What would and so that plus HBr, what would the intermediate look like?
You would have a positive sign over that secondary
Good.
carbon.
Over the secondary carbon. Right here, right?
Yeah.
So that's the intermediate. And then what would the 1, 2 product be?
One, two.
So bromine is here.
You'd have the bromine coming out of the secondary.
It just attacks here, right?
Yeah.
So if bromine attacks directly at the secondary carbon, then we're going to get the 1, 2 product that looks like this. That's not enough room. Yeah. Oh, I hate notability. For today, I do anyway. You'll get that, right? As the 1, 2 product. And then the 1, 4 product would look like, I draw it that way. this, right? Where the double bond gets shifted here. Because bromine is going to attack here, and then this is coming here like that. All right, so that mode of that mechanism will give me the 1,4 product, and it looks like this. All right, any questions? We covered a lot. So do you have any questions about anything that we covered? All right. So if there are no questions, then I'm going to let us go in peace. And I'll see y'all back here again on Wednesday. And if you don't have this handout, it's in Blackboard. It's under, if you click on assignments and class handout submission, it should be entitled, let me see what the title is. We should have had it because all the other stuff was on there too, but it's entitled New Conjugated Dienes 2019. So if you don't have it, you should get it. And then I'll see y'all back on Wednesday. I'll post this video to YouTube and I'll put the notes on Blackboard as soon as I can.